Okay, so at the beginning of last week, we were told, so I was here for the KITP workshop, to make some slides to talk about, ourselves and what we're here and what our interests were. And I never got to show them, so I thought I'll start off with that here. So I'm interested in type 1a supernova explosion models, 3D hydro models and nucleosynthesis, but also then observable signatures of these models and how to compare our models to observations. So these late-time light curves we heard about is something near and dear to me, and radioactivity, here radioactive decay lines of vanadium-48, and sort of chemical evolution, manganese, produced mostly in the more massive white dwarfs, and what impact does that have? What can we learn from observations of stars in the galaxy when we pull the abundances out of the atmospheres? In the last few years, I sort of been doing a lot of this stuff. I have few observations of supernova remnants. So that's the new spectrograph behind me there, and that's kind of what I'll talk about today. Basically, optical emission lines of the shocked ejecta in young type 1a supernova remnants. This is prior to 2019. We didn't know about this. It was all X-rays, right? You see the ejecta in 1As, but not in optical. The optical images or pictures you see from type 1a remnants, it's basically always the shocked from the forward shock, radiative shocks and sulfur 2 and things like that. So basically studying CSM or ISM, but not the ejecta. All right, so the big question I'm trying to address with this is, what are type 1a supernovae? And Chandrasekhar mass, for example, delayed detonations, or subchandras, emerging white dwarfs. And the person that put me onto this problem, got me interested in all of this, passed away this year. So just quick memory of Jim Trurin. He was my advisor in Chicago. I started with him about 20 years ago. Learned a lot from him, not just about science, but also how to, have a good work-life balance and enjoy the work if you can, and not to take myself too seriously. Right, so that's that. So we had a bit of this already, so I don't want to get into too much detail here, but just some models on the left of basically the Chandrasekhar mass explosions with the deflagration first, expanding the white dwarf before the detonation completely disrupts it, and on the right, the violent merger induced detonation in a double degenerate model. So, main point on the left here is it's about Chandrasekhar mass, and on the right we have sort of a range of masses, but around the solar mass or so of the primary. I don't want to get, yes, there's many other models. This is just illustrative. I'm not actually talking about this in this talk very much, so let's just move on. And I think previous speakers have sort of gone into some detail there already. So there's a new diagnostic, and this is optical coronal line emission of the reverse shocked ejecta in young type 1a supernova remnants. So what does this mean? Well, it means it's a fresh view on these supernova remnants. It's basically a new way of looking into the ejecta, and at a different time, right? Nebula spectra would give you, hundreds of days or years, and then, now we're looking at hundreds of years. You can do that with X-rays too. Optical has some advantages. X-rays have other advantages, but optical has some advantages. For example, better at the time still, better wavelength resolution. So coronal lines, what do we mean by coronal lines? Well, they're just named after the solar corona, because these lines were first seen in the solar corona. Here with a coronagraph, this is the sun, and then you see sort of, 5303 and iron 15, or the calcium 15, 5694, or the iron 10, 6374. We see the same lines. The physics is related collisional excitation of highly ionized species that emit an optical. And so the strange thing, well, it's a bit non-intuitive maybe, but these are low-lying forbidden transitions that are collisionally excited, but they're in very hot plasmas that are like tens of millions of degree hot. So you would think there should be, why do you get optical light, which you more associate with maybe 5,000 degrees, right, a black body spectrum. But it's just, the atoms are complicated. Some collisions aren't very energetic, or it's a cascade, or, so the atoms still transition, populate these transitions and give you optical light, even though they're collisions of, 14, 15 times ionized iron in a 20 million degree plasma. So those are coronal lines. That's what I mean by coronal. It has nothing to do with the corona. Where we apply this to is just the name for them. And so reverse shock ejecta, what I mean by that, so I just ran downloaded this SNR-Pi. It's an ISO 1D tool from Dennis Leahy, calculates supernova remnant evolution. The dash, don't pay too much attention to that. It's the set of Taylor time where you basically transition from, a free expansion to the, radius increasing as time to the 2/5 power, the set of Taylor self-similarity solution. And so the forward shock moves out, into some medium, and it starts accreting some of this medium. And, by Newton's laws, there needs to be, a reaction to this. And so, that's basically the reason for the reverse shock formation. So the reverse shock forms as a reaction to the forward shock sweeping up the CSM. And it basically communicates to the free expanding ejecta inside of it that there is something out there, and it shocks the ejecta. Now this is done in radius, so you see in mass coordinate it's always moving inward, but because everything's expanding, initially the reverse shock is sort of carried outwards because the expansion velocity is greater than the reverse shock velocity relative to the ejecta. But eventually things slow down, and the reverse shock accelerates inwards, and eventually it moves in and it reaches the center and it shocks all the ejecta, even the very slow expanding one. And so behind the shock, so this shock moves in, this one moves out. Behind the shock, you have shocked ejecta, and that emits an optical line. So let's go to the LMC. Here's the LMC. And here's a supernova remnant. It's SNR-01P. Just off my mic. And it's very young, maybe 650 years old or so, which we know from light echo modeling. And here's in blue H alpha, so that traces the forward shock. And in red, some broadband Chandra X-rays dominated by iron K alpha emission. So this is very hot shocked ejecta. And then if you put mu's on this field and you look at the wavelength of iron 14, so this is just schematically forward shock, reverse shock moving in. In 2019, we found this emission. It sits inside the iron dominated X-rays, but still outside where we think the reverse shock is. And it's this intermediate ionized iron, right? Iron 14, 13 times ionized iron. And so from the yellow dot there, and just extract the spectrum, this is what it looks like. It's a very broad line, about 2,500 kilometers a second. So it's a non-radiative shock. So radiative cooling has not led to this cooling instability mentioned earlier today. Basically, the shock velocity is imprinted into the width of the line. There's another remnant, even younger, SNR 509, minus 67.5, same color scheme, H alpha, broadband X-rays, and same thing, a nice thin front here. Here there's multiple shocks, and so it's a bit broadened, broad, but an even broader line, younger remnant, more energetic explosion, faster reverse shock. The width here is about 4,400 kilometers a second. So some back of the envelope estimate. So we have a collisionless shock. So it's not collision between the atoms, that, the ions that give you, the discontinuity, but it's interactions of the ions with the magnetic field kinks. And so we get mass proportional heating. So KT is 3/16 m times the shock velocity squared. But behind the shock, we have an ideal gas law. So from energy conservation, we can relate the width of the line to the shock speed. So it's just 4/3. And although the shock itself is collisionless, of course there are collisions, right? And that's what gives you the broad lines. And so I call this supernova remnant tomography because we can image the supernova remnant in sections through the use of penetrating waves, which in our case is, I guess, optical photons. And why do we image different sections? Because the reverse shock moves this way, and behind it, right, there's a different. It takes time to collision ionize iron. I'll show you some timescales next in my next 10 minutes or so. And the iron 9 is closer to the shock than the iron 10, and the iron 13 plus, which gives the iron 14, is even further away. And there's some separations here. And the good thing is we can resolve these separations. So here, iron 9, like 50 years. Iron 14 would give you like 200 years. Sulfur 12 is like almost 300 years after being shocked, right? Because it takes so much, there's so few collisions, it takes so much time to get that ionized. So remember these colors, this is blue, this is green, this is red. And so blue, green, red, they sit the same way, behind the reverse shock. And we can resolve these length scales, these tens of parsecs, tenths of parsecs. So 1 parsec over 10 is like a mu spaxel at this distance. So we can actually resolve this incomplete shock structure. Right, and so we can have model constraints, right? The ejecta mass, kinetic energy, and ISM density, they're the key parameters that govern the evolution of supernova remnants. And so for the fixed time, the forwards and reverse shock positions and velocities, they constrain these model parameters. And so we've done that. So Martin Lamming has used the Blasphemer code to model these the emission in these remnants, and we basically found that for 0509, for how young it is, the age is constrained by light echo models, and for where the location of the forward shock is, where the location of the reverse shock is, and the forward shock and reverse shock velocities. The only way to match it, we can't match it with a Chandrasekhar mass, so we need a subchandra. And this is very interesting because of 0509, we know the subtype of it, right? It was 1991 T-like. And so I know there were a lot of talks today that said the 91 T-likes, they're maybe the Chandra ones, but that's not what we found from this. We found that the 91 T-like one is best explained by a subchandra model. And so I guess you run out of time. So yes, this was subchandra, but you might say it was 91 T-like and had a high ejecta mass. And so yes, that's true, but even like a 1.1 solar mass, detonating zero white dwarf can give you enough energy and make enough, have still some left over for a bit of silicon. All right. Just real quick, and I'm out of time. I just want to flash this spectrum. So we have much deeper observations of 509 now, and now we see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of these lines. There's iron 9, sulfur 12, iron 15 that we knew about before, but there's also calcium now, some nickel 12 line. This one, not sure, it's iron 6, or might be a nickel 15. So there's this whole wealth of information there now that's a bit underexplored. And so the last 15, 20 years, whatever, I've been sort of doing this, modeling, this pipeline to model optical spectra of supernovae. And so in the future, currently, I'm sort of working on this, trying to do a similar modeling flow to basically predict the, let's call it, the nebular supernova remnant spectrum in optical and try to link that back to the explosion models. So thank you. Just to summarize, optical emission from this incomplete reverse shock, right, can be used to study type 1a supernovae. I'm not quite sure yet how, but I know it can. And we started it, but we're not quite really mature yet with this approach. But first outcome was 519 was well matched by a Chandrasekhar model, and 509 was best matched by a sub-Chandra model. And I thank you for your patience as a chair, the invitation to talk, and all of you for coming to my talk and sticking it out before refreshments. Thanks.
The patience was beginning to diminish. Do we have any questions?
I knew there wouldn't be any questions, so I thought I'd just...
Is there any hope of finding coronal lines from, say, nickel or manganese or some of these other elements?
So we already have nickel here. It's very faint, so these units are 10 to the minus 20, ergs per square centimeter per second per angstrom. But it's there, and I actually, so Ralph Sutherland, he ran the model. I thought this was also nickel. There's also nickel lines in the infrared, and so with JWST you would have a lot of more sensitivity. Maybe there's also silicon lines in the infrared that I think we can get. So manganese, I don't know. They're probably there. Depends how faint you can go. We haven't seen any, and haven't quite, I haven't seen one on the line list yet either that I'm like, oh, this one's probably going to pop out. But nickel for sure.
Can you use that to constrain?
Yeah, well, we're still building this whole pipeline to somehow, this is so far, this shock is just a planar shock running into, it's not a self-consistent model 3D evolution kind of thing where we want to get to really link, but this is the, that's the dream anyways.
Ivo, so all of these, so I have two questions. One is, are these lines produced in like temperatures of 10 to the 7 Kelvin gas, or is it?
Yes. Yes.
Okay, X-ray. Okay, and the other thing is, are you getting like your full width half max plots and all of that? Is that from integrated over the entire shell, or is it location by location?
This is just one location. Yeah, everything I've shown so far is just one location. If you sum it, because you get like Doppler shifts where you see the front and the back, and it would be much broader and sort of more confusing. I haven't shown some things. Like the iron 10, for example, looks it's just on the outside very, and then the calcium looks all clumpy, for example. So there's information there, and I think the iron line, which now looks very strong, and sometimes it seems like it splits. So you see front and back at the same time. So there's a lot confusing things. It looks pretty like this, but of course this was cleaned a bit as well. I had to do some Savitsky-Golay filtering. It's really faint, but that's basically the answer, right? It's super faint, and so we're working at the limit of, this is like 30 hours of muse on target.
I remember reading in some remnant paper that the adiabatic index in the shock material isn't always ideal gas, isn't always 5/3, because cosmic rays can propagate out and make it squishier. Do you know what I'm talking about, and does that matter?
I know what you're talking about, and the back of the envelope was just that. It was just the back of the envelope calculation. There's other problems with. I think a bigger problem for us is, iron electron equilibration. Right after the shock, right, we have this mass proportional heating. The electrons get shocked, and the ions get shocked, and the iron is very hot, and the electrons are not so hot because they're way less. Because it's collisionless, right? They don't talk to each other. They're each their own at their own temperatures. And there's some, there are collisions, so at some point you start to equilibrate. Other things we don't really know is, normally people talk about, this excitation of these lines. It's always some metals in hydrogen plasma. This is not a hydrogen, it's not even a metal-rich plasma, it's just a metal plasma. There's no hydrogen, and so these collision excitation and ionization rates between things like iron and oxygen, they're just not well known, I think. So we're more worrying about stuff like that at the moment than cosmic rays propagating back, which has an effect on the evolution of the remnant for sure too. It drains 10% of the shock energy might go away, but we're not quite there yet. We're actually very, in the infancy still of even we just discovered it now. Now we're trying to figure out what can we learn from this. And I look at the spectrum, I think we can probably learn a lot. But
yeah, great.
But I don't know what
yet.
yet.
Looking forward to it. All right, thanks, Ivo.